Hello, I'm Patrick Holberg, and this is a short video about the Solow growth model. The Solow growth model is trying to explain the growth of per capita income. Of course, so what we're thinking about here, when you look at this picture, we are thinking about defining the level of development by per capita income. Of course, in general, the level of development is something more holistic, including income, education, health, as well as levels of poverty and inequality. But the neoclassical model focuses on income solely. So we're trying to explain how countries increases their level of per capita income. In a bigger picture, we see that a country's historical experience will help explain that, because historical experience, especially colonialism, will determine the country's institutional framework, and the institutional framework will give the or set up the incentives that operates within those the economies of those countries. And of course, what we are thinking about here is this black box right here. What kind of economic policies should we put into this black box in order to achieve a level of development, and in this case, a high level of per capita income? Well, the sources of growth in general are capital, labor, and technology. So all these things should be going right into this black box to try to explain it. And there's other models that try to do this, but today we want to look at the Solow growth model, because the Solow growth model looks at all three factors at the same time. The approach of the Solow growth model is to look at a very particular equation, which is right here: y equals a times k to the power of alpha, L to the power of 1 minus alpha. And in this equation, we have, which is a Cobb-Douglas production function, but the A here represents technology, K represents capital, and L represents the labor. And this little alphas up here, alpha is the proportion of output that can be attributed to the capital, and 1 minus alpha is the part of output that is attributed to labor. But the most important thing when we look at this production function is that it has some very good properties, and this is why we always tend to use this Cobb-Douglas production function. The first thing is that it exhibits constant returns to scale. Constant returns to scale says that if you were to double capital and labor, so if you have twice as much capital and twice as much labor, then output is going to double as well. And that is true for any factor x. So if you scaled capital and labor by any factor x, output's going to increase by the same amount. So if we had this one, so if I wrote a times x k to the power of alpha, xl to the power of 1 minus alpha, we can simplify that, and what we get is x alpha plus 1 minus alpha to the power, times k to the power of alpha and L to the power of 1 minus alpha. And of course, x to the power of alpha plus 1 minus alpha is just x to the power of 1, so this is just x, and therefore what we have here is x times a k alpha L 1 minus alpha, x times y. And that is true for any x. In particular, if x was equal to 1 divided by L, what we get then is that a times k divided by L alpha, L divided by L 1 minus alpha is equal to 1 divided by L times y, which is equal, if I just simplify this, because L divided by L is 1, and 1 to the power of anything is equal to 1. So what we get here, therefore, is that output per person or per worker is equal to A times K divided by L alpha. And from now on, we're going to call this little y and little k. So the lowercase letters here represents per worker or per capita output. All right, so that's a good thing about constant returns to scale. We also have diminishing returns. And diminishing returns says that if you were to increase one factor, for example, if you were to increase K, then output will increase at a decreasing rate. So what that means is that if we have capital here and output here, as you add more and more capital, output is going to increase, but at a decreasing rate. So we get this shape that we have seen before in production functions. All right, so those are two very important properties of the Cobb-Douglas production function, which is the main equation for the Solow growth model. And we can use these then to explore what happens to output as we add more capital, more labor, or improved technology. And that's what we're going to do just for a few minutes here. I like to explore the Solow growth model in 3 steps. So in the first step here, let's think about capital. So right now we think about how would capital increase. Well, there's some things we have to remember about the Solow growth model. One is that it is a closed economy. So if we want to invest, so if this country wants to invest, then we have to save. That's the only way to get around this. So savings equals investment. At the same time, we're now going to define savings as some savings rate. This little s here is a savings rate. So the proportion of output that is being saved gives us national savings. So that will be S. So little s times y is S, which again equals investment. And that investment, and this is very important here, can go into can achieve 2 things. First of all, that investment can add more capital to the entire economy. And that is, of course, what we're really looking after. But at the same time, some capital every year is going to be depreciated. So before we can add more capital, right, so before we can have an increase in capital, delta K, we first must replace all the depreciated capital. All right, so this is what we're going to do. So if I just simplify this a little bit, and because we have constant returns to scale, I can make everything into per capita form. So what we have here is that savings per, out of income per person. So savings out of this has to be split up between the creation of new capital. So we have new here. And we also have to replace the depreciated capital. All right, so in particular, before we can start giving the workers more machines, we have to replace all the machines that were depreciated away over time. Clearly, since what we're really interested in is this change in capital. So if I just rearrange this a little bit, we can see that the change in capital depends on whether or not the savings per person is greater or smaller or equal to the depreciated capital per person. And in particular, we can clearly see that the only way we can have more capital per worker is if you save more per person than capital is depreciated away. Now, the way we solve the Solow growth model is to look for a steady state. And a steady state has a very, very particular definition or interpretation. So what we really mean with steady state is that the key variable, which in this case is capital per person, so the key variable is not changing. If the key variable, capital per worker, the capital labor ratio, is not changing, then we have what's called a steady state. And clearly that can only happen if what we invest or save per person is equal to the depreciated capital. All right, so this is what we're looking for, and the way we usually do it is to draw a diagram. the diagram here, on the two axes, I have put capital labor ratio and output per person. Of course, what we're trying to do is to figure out how to make this y here, the little y, output per person, as large as we possibly can. Alright, so what I want to do here is just draw in our diagrams. So first we have our production function, and everything is in per capita terms here. So the production function, because of diminished returns, has this shape. So y equals a times the little k, capital labor ratio, to the power of alpha. But when we think about steady state, we need to look at the savings per person. So we draw in the s times little y here. And then finally, I just have to draw in a line that shows how capital per labor is depreciated. So this is our depreciation line. And clearly we can see here that a steady state is achieved when they are equal to each other. That's what we just said on the previous slide. And from that equilibrium, we can find our steady state capital labor ratio. If you know the capital labor ratio, you can just plug that into our production function. Find that line, go read it off, and this will be our equilibrium or steady state per capita income. Alright, so this is really good. We can see what our per capita income is depending on our steady state. But there is some problems here, something we need to keep in mind. So what we're saying here, that when we get to, in the long run, we get to this steady state, and at that point the capital labor ratio, so K divided by L, is not changing. So this is constant. Now the only way capital labor ratio can be constant is if K and L are growing at the same rate. And since right now we have that the rate of growth for labor is 0, therefore the growth of capital must be equal to 0. And if capital labor ratio is not changing, then output per worker is not changing, which also means that output growth is equal to labor growth, and they're both equal to 0. So this, when we just think about capital accumulation in the long run, this is not very interesting because we just get the answer that there is no growth in the long run. We're going to get to a steady state and then everything stops. Output per person is not growing. So capital alone cannot explain long-run economic growth. Now, before I switch over and add labor and then later on technology to this story, note this though, that if we were to start at a capital labor ratio that was much lower, like K1 over here, at this lower capital labor ratio, we can see that our saving is greater than our depreciation of capital, and therefore the change in capital would be equal to or greater than 0. So what happens then is that as long as we are to the left of the capital, steady state capital labor ratio, our capital per worker is going to increase, and we're going to be moving towards this steady state. But again, once we get to the steady state, everything stops and we have no more economic growth. Okay, so in step number 2, we want to add population growth to our capital accumulation. So what we do is we assume that population is growing at a steady rate, and we can call that rate n. So every year population increases by the rate n, say 2%, 3%, something like that. And what we have then is that whenever we save, we're going to have to replace the depreciated capital, and we have to give all the new workers the same amount of capital, and if there's anything over, then we'll have a change in the capital labor ratio. So again, we start out here, so this is how much we're saving per worker, and out of that saving we first have to replace the capital that depreciated over the time period. And then we have to give all these new workers the same amount of capital as all the previous and all the old workers had. So we have to give them all the same amount of capital per worker. And again, if there's anything left over, then we have an increase in capital per worker. So this is what this one says. So we'll have an increase in capital labor ratio if and only if we are saving more than what we need to replace due to depreciation and adding new workers. We're using the same solution method as before. We're looking for a steady state, and the steady state is defined as there is no change in a key variable. So here again the capital labor ratio is staying exactly the same, and that must be true if we are saving the same amount as we need to replace due to depreciation and adding new workers. We can once again see that in a diagram, which is what we're going to do next. Okay, here we have our diagram. Everything is in terms of capital per worker and output per worker. And like we had before, we have our production function, which has diminishing returns. So this is our production function. We're saving some rate out of that. So if I add our rate of saving, this little s, and multiply that by y, this is going to be our saving. But now what we have is every year some capital is depreciated, and we're getting some new workers. And our steady state is therefore defined when we are saving just enough to replace the depreciated capital and giving all the new workers the same amount of capital. And this intersection here gives us our steady state capital labor ratio. From that steady state we can derive our output per person, which is really what we are interested in here. And that's it. This is what our output per worker would be in steady state in the long run. Of course, you can notice here, this is an interesting thing, that if if the population growth rate was to increase, so if we had a higher population growth rate, you can see that we'll have a lower steady state and therefore a lower per capita income. Conversely, or inversely, if we were to have a lower population growth rate, then we can have actually a higher per capita income. Okay, so right now though, we are thinking about we're thinking about the steady state, and in that steady state, as we have seen before, the capital labor ratio is not changing, and therefore capital and labor are growing at the same rate. Now we know that labor is growing at the rate n, and therefore capital must be growing at the rate n. But the capital labor ratio is not changing, which means that output per worker is not changing, which means, again, that L is growing at the rate n, and now output is growing at the rate n as well. So what we see here, and this is somewhat interesting, is that we can explain an increase in output now, so we can see why output is increasing, but we cannot explain an increase in output per person, or there will be no increase in output per person. Alright, so once again, this is where we're at. Next step is to add technological growth, and maybe that can give us an increase in the output per person over time. Sustainable economic growth, the way we would like to define it. Okay, so this is step 3. Now we are adding both capital, labor, and technological progress to our model. And as you recall, this is our production function, and we can see all three factors here. We have A, that's our technology, we have K, that's capital, and we have L, labor. Now what we're going to do is give a definition to our technological variable right there. So we're going to say A equals E to the power 1 minus alpha. The reason we have 1 minus alpha is because we want to combine that with our L over here. So we'll do that in a second. E is the efficiency of a worker. So what we're thinking about here is labor augmenting technological progress. So when we have technological progress, it is as if we have more workers. So technological progress makes each worker more productive, makes each worker more productive. That is, each unit of technology augments the labor supply. So it's as if we have more workers. All right, so what we do here is just, we put E into there and we rearrange, and if we do that, we get this expression of our production function. And then we just do what we did with labor. So this is constant returns of scale, so we can multiply these factors by any factor x. If we let x equals 1 divided by E times L, we get that output per effective worker is equal to capital labor or capital ratio per effective, or capital per effective worker to the power of alpha. Let me write that again. So what we have here is that y divided by EL is now equal to capital per effective worker to the power of alpha. All right, so this is our new main equation. And like we've seen before, it's easier if you write that in, small letter or lowercase letters here. So this is not the same y because I have, there's this hat to denote output per effective worker and a hat over the K to denote capital per effective worker. All right, so if we move all these things away, we can see that if we want to change, if we want to have more capital per effective worker, this is what it's going to take. We have to, of course, save out of that effective output per effective worker. And then that's going to first replace depreciated capital per effective worker, the increase in actual number of workers, and then we have to give all the workers in the entire economy the new technology. So we have to first give all the new technology before we can actually increase technology per person. So this is our thing, and as always, we're looking for a steady state here. The steady state will be defined as there is no change in the capital per effective worker. That is, there is no change in our key variable, and in this case the key variable is capital per effective worker instead of just labor. And that's going to be true if we save equal to what is being depreciated or what we have to add to all the new workers coming in. All right, so that's pretty, this is how we solve it. Next we go on and we look at the diagram. First, here's the diagram in terms of effective workers. So now here, everything here is capital per effective worker, and this is output per effective worker. And we find a steady state, just like we did before, where the two lines intersect. It gives us our steady state capital per effective worker ratio, which then gives us our steady state output per effective worker. The problem is with this, this is, looks nice and everything, but here we are finding y divided by EL, but what we're really interested in is y divided by L. Standard of living, output per person. That's what we're really trying to explain. So let me go on to another diagram where we keep our variables to be per worker, not per effective worker. All right, so here is everything in per worker, capital labor ratio, and output per worker. And in this case, we have our standard production function, y equals a k alpha. Note here that now I have A here because I have not taken that away yet. And we would have our saving, we would have our depreciation plus new workers, capital line, and we would have our steady state right here. And what I'm trying to do in this diagram is show you what happens if we have technological progress. So if A equals e to the power 1 minus alpha, what happens as E is growing at the rate of G? You know, if this is always growing at a rate of G, what would happen to our picture right over here? Well, what happens is, of course, that if E is growing at the rate of G, then next period A will be greater than A before. That is, we have better technology. And the impact in our diagram is that our production function is going to be shifting up like this. And if that shifts up, then our savings function will shift up as well, because we'll have a different y now. And you can see now that our steady state is going to be increasing. Basically what happens is that at the original steady state, after improved technology, we will actually be saving more than we are depreciating out of the capital stock, and therefore we will start moving towards a new steady state. And as that steady state increases, we get output level that is higher than it was before. Sorry for the crooked lines there. So, you know, we have now a higher per capita income. And this will be true as we, you know, if every period technology is going to grow at a rate of G, and therefore this one's going to be shifting up. Our savings function is going to be shifting up. Going to put us on a path to move to a new steady state. At that steady state, we'll have a higher output per person. So what we see here is that technological progress allows output per worker, this little y, to increase in a sustainable long-term fashion. All right, so finally we have explained how output per person, standard of living, can increase over time. And and what it requires is a steady increase of A, which we just assume is constant at this rate G. Alright, let me just quickly sum up everything we have learned, or a few things that we have learned, and what we can see in these slides. So the first thing that I wanted to highlight was that variations in income per capita levels. All right, so this is not the growth rate, but this is the level. So this is, you know, why are some countries rich while others are poor? According to the Solow growth model, the differences in income per capita levels across countries can be explained by differences in the savings rate, in the population growth rate, and maybe the rate of depreciation, although we usually think of that as being constant. As if you go back and look at some of the previous slides, you can see that rich countries will have a higher S and a lower N than less rich countries. Alright, the second thing we can see that we can have growth in the medium run if a nation or an economy is moving from one steady state to another. So what this implies here is that, you know, if we were to give advice, for example, and we say, increase your savings rate, that would increase a steady state, but in steady state, the growth rate of output is always equal to 0. All right, so the growth rate of y would be equal to 0. But before we get to this new steady state, there will be some growth in the medium run. So you have growth as you go from one old steady state to the new steady state. But when you get to steady state, growth would stop. And the same would be true if you were to lower the population growth rate, then you can get a higher steady state, and in the medium run, you will grow to that new steady state. All of these, changing savings rate, changing population growth rate, gives us no impact on the long run growth rate. If you want to grow, growth in the long run requires technological progress. So the only way that we can grow in the long run is if our A variable is increasing. That will shift our production function up continuously, and that shift up will always ensure that we are never stuck in a steady state. We keep moving to a new steady state every time period, and that movement, which is really making the medium run growth rate continuous, is what allows us to grow into, sustainably into time. But a very important thing about the Solow growth model is that this technological progress is left unexplained. This is why we call this an exogenous growth model. That is, at the end of the day, we say that growth in per capita income is due to technological progress, but we don't explain how technological progress actually happens. All right, that's the end of the Solow growth model. Thank you very much.